Hello, I am Seema and welcome to part 26 of the chapter Organic Chemistry, Some Basic Principles and Techniques. In part 25, I explained resonance structures to you. In this video, I'm going to explain 3 solved examples so that resonance structures becomes clearer and the concept really solidifies in your mind. So let us come to the first problem. You have to write the resonance structures of CH3COO negative and show the movement of electrons by curved arrows. We've done curved arrow notation to show the movement of electrons. As for writing the resonance structures is concerned, we did it in the previous video and I told you how when you're writing down resonance structures, what are the points that you have to keep in mind. First of all atoms, that is all nuclei, they have fixed places. You do not change the position of atoms. So the nuclei, they have the same place, and that is the first point that you have to keep in mind when you're writing down the resonance structures. The second point is that all atoms that should have the same number of unpaired electrons, or rather not all atoms, the total number of unpaired electrons in the structure should be fixed. And if you take the different resonance structures and you want to find out one of them which is more stable, or you want to identify the most stable resonance structure or the most contributing structure in resonance, or which leads to the maximum lowering of the resonance energy, that structure would be one which has the maximum number of covalent bonds, 1, right? Then secondly, all atoms other than hydrogen should have their octets completed in that. There should be a less separation of charges, and if there is a separation of charges, then the negative charge should be on the electronegative atom and the positive charge should be on the electropositive atom. That will be more stable rather than a species or a structure in which the negative charge is on the on the electropositive atom and positive charge is on the electronegative atom. Imagine, it is somewhat like there's a person who is naturally very agitated, is always angry and he's always thinking about him, he's always fighting about something. All of a sudden you come to school one day and you find that person is just sitting quietly in a side, and is not saying anything to anyone. There is no, mission, there's no zeal in him. So what do you feel about that person who is normally so agitated and all of a sudden one day is very quiet? On the other hand, there's a person who's very silent, very calm, has a very nice demeanor, very peaceful demeanor, and one day you come to school and you find that that person is really agitated, is picking up fights for no reason, is angry, or is very happy and is dancing about, and it could be anything, is extremely excited about something. Both of these are not natural to them. So when you see something that is out of normal, that is not a very stable state. You would not feel that that person is stable. One who is always fighting is suddenly very quiet. You feel a little uncomfortable about that. Similarly, one who is always quiet is suddenly fighting. You feel uncomfortable about that also. So a state that is, it would not be the normal state. Anything that is out of normal would be a more energetic state, or we would say a little unstable state. That whatever that person is like, he's going to go back to his normal nature. He's not going to remain in that abnormal state for long. So an electronegative atom should have the electrons, and an electropositive atom normally would be positively charged. So if the negative charge is on the electronegative atom, that is a normal behavior. But if on the other hand it is on the positive electropositive atom, then that is abnormal, which means that it is not a very stable state. Right? So you have to see that there should be less separation of charges, and if there is separation of charges, then the atom that is more electronegative should bear the negative charge. And the more the dispersal of charge, the more stable is that structure. So if the charges, the positive and negative charges, are not sitting at one place, the more dispersed it is, further off it is in a single structure, the more dispersed it is, the more stable would be that structure. So keeping these points in mind, let us now solve the question. You have to write the resonance structures of CH3COO negative. We know that all atoms should have their octet complete except for hydrogen, which has its duplet complete. So carbons should form 4 bonds because it has 4 electrons in its outermost shell, and therefore it should form 4 bonds. So in CH3, carbon is forming 3 single bonds with hydrogen, and each of the hydrogens has 1 electron and forms 1 bond with carbon, therefore the duplets of hydrogen are completed. Hydrogen usually, if it forms a single bond, is satisfied. What usually it always forms only single bonds and is satisfied. Its duplet is completed. Carbon, on the other hand, should form 4 bonds. So if you have CH3, the 2 carbons will be bound to each other and the oxygens are connected. Now, oxygen has 6 electrons in its outermost shell, and in order to complete its octet, it must form 2 bonds, right? So 2 of its electrons should form 2 bonds. So let us make one of the oxygens, let us satisfy it with 2 bonds. So now oxygen had 6 electrons. It used 2 of its electrons to form this double bond, and therefore we now get this. Now there's a problem. This oxygen should also have its octet complete. But carbon has already completed its octet by forming 4 bonds. 2 single bonds and 1 double bond. Therefore carbon is not going to form any more bonds. Right? So if carbon is not forming any more bonds, then obviously this oxygen had 6 electrons, 1, 2, 3, 4, 5, and a 6th electron it had. It used 1 electron to form the bond, therefore it now has 7 electrons, therefore it gains 1 electron from the other species which must be attached to it because this is an ion, and that electron, since it belongs to another atom, this oxygen will have a negative charge. Right, so this is the structure of CH3COO negative. Now let us imagine that we want to make its resonance structure. The resonance would be between the 2 oxygens because CH3 and C is stable. It is this oxygen which can show a little jump of the pi electrons. The double bond can shift from here to here. So how does that happen? The other structure, resonance structure, would be again CH3C. Now this oxygen, let us say if I make the 2 electrons here, yeah. If the pi electrons, they move here, what will we get? We'll get C, this will become a single bond, oxygen here, 1, 2, 3, 4, 5, 6. And since the electrons of both the electrons of the bond have moved to oxygen, one of the electrons actually belongs to carbon. Therefore, this oxygen now, due to these 6 electrons that it has, 1 of carbon, it becomes negatively charged. At the same time, as 1 electron goes from here, this negative charge, it tries to overcome or help out. So this pair of electrons comes here and results in the formation of a double bond, resulting in 4 electrons here because 2 of the electrons have gone, and at the same time, since these 2 electrons went down here back to carbon, the negative charge was lost by this oxygen. So these will be the 2 structures that you will get when you try to make the resonance structures. Write the resonance structures of CH3COO negative and show the movement of electrons by curved arrows. So you showed the movement of electrons by curved arrows. The same thing is going to happen if it has to shift back to that. This will come here and the negative charge would come back here, and here the pair of electrons would move here and result in the formation of a double bond. So these 2 structures would keep interchanging among each other. So this was question 12.16. Let us now come to the next question, that is question 12.17. You have to write the resonance structures of this molecule, that is CH2 double bond CH-CHO. And you have to indicate the relative stability of the contributing structures. So let us first write the structure in the middle. You have CH2 double bond CH. We'll assume that the H is here and the bonds are between carbon, and hydrogen, but oxygen has a double bond here. You see this? The oxygen should form a double bond. Why? Oh, this should be a hydrogen, H, right? And if I write this hydrogen down here, it will be clearer to you the number of bonds that it is making. Carbon is here, this is a hydrogen here, and these 2 hydrogens. Now, each carbon should be forming, if you look at this structure, what is happening? Each carbon should have octets completed, each hydrogen should have its duplet complete, and oxygen should also have its octet complete. Carbon has 4 electrons, it forms 4 bonds, it's forming 2 bonds with these 2 hydrogens. If I wanted to write them separately, I would have shown you that this is 1 hydrogen, this is 1 hydrogen, carbon is forming 4 bonds. Look here, here also carbon is forming 4 bonds. Look here, it is 2 plus 2, 4 bonds. So every carbon is forming 4 bonds, hydrogens are forming single bonds, and oxygen has 6 electrons in its outermost shell. Therefore, it is understandable that if it has 6, in order to complete its octet, it should form a double bond. And that double bond would be with this carbon. And it is only after you do that the octet of carbon would also be complete. So, in order to understand this, CHO, the structure is such that carbon forms a double bond with oxygen and a single bond with hydrogen. So this is the molecule that we have, and these are the bonds that we have. And this is what we are going to start with, and let us see how are the pi electrons going to shift, how are they going to move in order to give us resonance structures. There are 2 possibilities. Since you have 2 double bonds here, the double bonds can either, this double bond can either move, the electrons can move up to oxygen here. So let's make one structure here. If these move to this oxygen here, you have CH2, I'll write H2 as it is, assuming that you understand this. CH2, and here I'll leave a single bond now, CH, C, this is a single bond, and this therefore has a negative charge, and hydrogen here, right? Now, as soon as the negative charge went here, the double bond here, what will it do? It will try to remove the deficiency, and it would move, the electrons would move to this direction. And when that happens, when the electrons move to this direction, the double bond comes here, right? So, as the electrons move to that direction, the 2 electrons move to this direction, the double bond comes here, and this CH2, it acquires a positive charge. Is it clear? Now let us assume that instead of the electrons moving towards oxygen, if the electrons had moved from oxygen, from this double bond to this position, then what would have happened? Then the electrons, instead of, if electron density is increasing here, then it will lead to repulsion on the other side. So these electrons, instead of moving here, would move away. Right? So what will happen? If that happens, let us assume now the opposite is happening. Let me show it with curved arrows, or let me use another color. Yeah. So now in this step, what is happening? A second bond from here is shifting here, right? If the second bond is shifting here, what will we get? We'll have the CH2, CH, CO, and this bond has moved here, so we get a double bond here, right? Since we get a double bond here, what happens to these electrons? Too much carbon cannot form 5 bonds. It had 1, 2, 3, 4. So the moment a second bond is formed here, one of these bonds will now move to the next carbon. So these 2 electrons will move towards carbon. And the moment it moves towards carbon, the carbon becomes negatively charged. Right? The 2 electrons move to carbon and it becomes negatively charged, and this oxygen, since it lost the electrons, you'll have 1, 2, 3, 4 here, right? So since it lost the electrons from here, therefore this oxygen would become positively charged, right? And since it became positively charged, it had 1, 2, 3, 4 and 5, yes. One of the 6th electron that it had, that electron has been lost and it has come here. Therefore, this oxygen is now positively charged and this carbon is negatively charged. So these are the different canonical forms that you will have. So this was one structure. This was the second structure. I should have made it a little lower in order to be clear that this is the structure. Anyway, it's too close, you'd still understand it. This is your... I should shift it down. So you have H2, C, double bond C, O, H, And this oxygen, since it has lost the electron, this becomes positively charged with 1, 2, 3, 4 electrons. And this carbon, it gave its electron here, so this carbon becomes negatively charged. And what do you have here? H, right? So these are the two structures, the three canonical forms that you will get. So you wrote the resonance structures of this molecule, and you have to indicate the relative stability of the contributing structures. What did we study about the relative stability? That the stability of that structure is more where first of all, what were the different points? That among the resonance structures, the one which has more number of covalent bonds, which has less separation of charges. We see in this structure there is no separation of charges, right? And it has more number of covalent bonds. Do you see it has 2 double bonds? So it has more number of covalent bonds, there is no separation of charges, therefore this one is the most stable. So we'll say in stability, this is number 1. Most stable structure, because what are the reasons? That it has a maximum number of covalent bonds and there is no separation of charges. Now in both of these the number of covalent bonds is the same, but there is separation of charges. So now out of these two, which is more stable, how will we come to know? If the electronegative atom, by its nature, it should have negative charge. So if the electronegative atom has negative charge, then that structure would be more stable. So what is the electronegative? What are the charges between? Charges are between carbon and oxygen. Carbon and oxygen in both these structures. Oxygen is more electronegative. Therefore, when you have the negative charge on the electronegative atom and positive charge on the electropositive atom, that one would be more stable. So stability wise, this would be rated as number 2, and this is the least stable out of all the structures. Right? So these were questions. This was question 2.17. Now give me a moment to write down question 2.18. This is question 12.18. The question reads, explain why the following two contributing structures, 1 and 2, cannot be the major contributors to the real structure of CH3COOCH3. You know, for any structure to be a major contributor, it should be more stable. And if these two are not major contributors, it means that they are less stable. There is some reason why these are less stable. What are the factors that decide that a structure is stable? The first thing is that the structure should have maximum number of covalent bonds. Secondly, the octets and duplet of hydrogen and octets of all other atoms should be complete. The third point is that there should be no separation of charges. Fourth point is that if there is separation of charges, then the electronegative atom should get the negative charge and the electropositive atom should get the positive charge. And the last point here is that if there is a distribution of charges in the structure, then it is more stable, and more dispersal of charge, then it is more stable than the others. Now both of these structures are not stable, and we have to say why are they not stable. So that they cannot be major contributors. So we have to see points of instability. Maximum number of covalent bonds, right? This seems to have more number of covalent bonds here, right? Out of these two structures, if you take a look, this one appears to have more number of covalent bonds. Yeah, because it has a double bond, and here you have all single bonds. That's one thing. So this should be more stable in comparison to that. But yet they are both unstable. So let us take them one by one. Second point is that all of them should have their octet complete. And take a look here. Here you have carbon forming 3 bonds and bearing a positive charge, right? So oxygen here has 8 electrons, 6 plus 2 is 8, although it has a negative charge. This carbon is forming 4 bonds, 3 plus 1, 4. This carbon is forming only 3 bonds, and it does not have a negative charge or 2 negative charges to compensate for the 2 electrons that it does not have. So it has a sextet of electrons. Since it has a sextet of electrons, its octet is not complete, therefore this is unstable. And this cannot contribute to be the major contributing structure. It cannot be the main structure which is helping in resonance. It may be one of the structures, but it is not a major contributor. Then the negative and positive charge separation, if it is there, it is between oxygen and carbon is more electropositive and oxygen is more electronegative. Therefore, on this point it is okay that oxygen has negative charge, carbon has positive charge, so this is not the main point. So what is the main point here? That it has less number of covalent bonds than this, and second is that this carbon has a sextet of electrons, its octet is not completed, therefore this is not the major contributor. If you look for the drawbacks in this structure, the number of covalent bonds is more, therefore according to that point this would be more stable than this. But then there is another factor that comes in. There is a charge separation. So okay, the charge separation, good idea. All atoms are forming the right number of bonds, therefore the octets of all atoms are complete, therefore this should be definitely be more stable. But the one thing that is making it unstable and not making it the major contributing structure is that the negative and positive charges are on oxygens. Both the atoms have the same electronegativity. Yet one of them is bearing a positive charge and the other one is bearing a negative charge, which is not the true. Oxygen having negative charge is good, but this oxygen having positive charge is not a good thing. Because it is in electronegativity, it has the same electronegativity, yet one of them is bearing the positive charge and the other one is bearing the negative charge. That makes it unstable. So the charge, it has charge separation. There should be no charge separation in such a case, because if both the oxygens which are equal in electronegativity are bearing charges, therefore it has charge separation, and both the atoms of the same electronegativity are bearing opposite charges, therefore this cannot be the major contributing structure. And in this case there is charge separation, lesser number of covalent bonds, and one of the carbons does not have its octet complete. So these were the reasons why they cannot be the major contributing structures in resonance. So with this, the topic resonance structure comes to an end. I'll wind up this video here. If you liked it, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.